Hi everyone. Let's wait 1 or 2 minutes maybe again. So Maxim, what do you think? Shall we start now or wait a bit more?
Um, I don't know. I think maybe some people connecting.
All right.
Let me check.
Then I wait a bit more.
Yeah, 1 or 2 minutes, and yeah, we're good to go.
Okay.
All right, so I think we're good to go.
Yeah.
So yeah, when you want.
Cool. So this short presentation is I think one of the first presentation of the different racer in the donkey car community. I think Maxim, you can tell me, but there's also maybe a plan later on.
Yeah, we plan to do this more often. And yeah, if anyone has a great algorithm to show or a different approach to problem, they can contact us. I mean, my Donkey Kong maintainers, and we can set that to yeah for for a talk like this one.
All right. So today's talk will be more or less about what I've been doing for the last 2 years and a bit even more on the donkey car and also on the real racing robot, on learning to drive and learning to race with reinforcement learning. And as I don't know how much you know about everything, I will first give a short overview of reinforcement learning, and then I will dive into the details on how I managed to learn to drive in some minutes only, and how to learn to race, but this time with several hours. And I've been mainly working with a donkey car simulation, as most of you know it. Um, So the idea is you get a donkey car that you can control. You can control the steering and the throttle. And you receive different information about the car, and the main one being the onboard camera, which you can see on the top right. And to show you how it does look like in practice, this is the result after training for several hours, and this is what I'm going to present. Is you have a car which started from scratch and which learned to race on that track. And one thing to note about it is that even though it was not trained with the trees and with different lightning, it can manage to race anyway. So the idea is here: you have a car, you have a track, and you need to race as fast as possible on that track, given mostly the image as input and some information about your speed. So this is the result at the end, and of course the simulator is available at that URL. But first I would like to quickly go into what is reinforcement learning. So most of competitors for donkey car use what's called behavior cloning or imitation learning, which is you drive the car around several times, several laps, and then you train a model to imitate the behavior.
Marlene, dann würde ich jetzt fahren, ja?
Sorry, Rainer, I think your microphone is on, so please mute. Yeah, thanks.
Sorry.
Don't worry.
So as I was saying, most of the time, people are driving around and then trying to imitate the driving. The main issue with that is you need to be consistent, and you also need to be a good driver, which is not my case. So here the goal is to learn more or less from scratch to drive and then learn to race. And at the end, in fact, the car is driving much faster than I can, at least on that track. So how do we do that? We can do it using reinforcement learning. So reinforcement learning, the basic idea is you will let your robot do something into the world, and you will give it only some feedback if it's good or if it's bad, and you try to maximize all the good reward. So in practice here, you have an RL agent which receives as input the observation, which is a mix of all the information it can have about the robot, so the camera image, the speed, some acceleration information using the IMU. And the agent will predict and output some steering and throttle, which is sent to the motors. And then as a feedback, it receives the reward, which can be positive or negative, which tell it if it's doing good or bad. And then it gets also a new observation. So the environment is the place where the agent acts, and which is also computing the reward and giving the information. And yeah, the goal is to maximize the sum of reward and not just the immediate reward, because you want to be good on the long term. And to give you an example of a reward for learning to drive, for instance, you can just say, okay, if the car is still on the road, I gave a positive reward. And if it's not on the road, then I can just give a negative reward. So for more information and more details about how to apply reinforcement learning in practice, I recently gave a talk at the Reinforcement Learning Virtual School, and the video is online, the slides are online if you want to learn more about that technique and about the best practices to apply reinforcement learning in practice. And for instance, I gave 3 examples of applying it on real robots. So far, so good. Do we have any question?
For me, it's good, but maybe other ones have questions.
Antonin, in your previous slide, you showed that you're using IMU. or
It can be used, but it's just an example of what information you can give as input to your agent.
okay, but have you successfully used IMU before on the Donkey car?
So I'm not using it currently because I want to use as less sensor as possible because my real car in fact has only the camera, and I want to that everything that I do I would like to do it also on a real car. So I've not used IMU directly, but I've used IMU with other robots, if that's the question.
All right.
Hi, Anthony.
Thanks.
There was
Can you hear
another
me?
question? Yes.
Yeah. So do you mean that the minimum requirement of like doing this is just the camera image?
If you want to learn to drive, yes. If you want to learn to race, you need at least the speed. Otherwise, it's very hard to know how fast you are going, and you would need to kind of predict that, and that's not trivial if you don't have the sensor.
Okay. So I just saw your car. I can see that the camera is like it's quite similar to I think what is with the height is like is similar to the simulator. Is it intentional or is it just like how you would like it to be set?
I think there's different reasons of why it is like that. The first thing is the car was created with a friend before I started using the simulator, so there's it's not intentional that it's the same height. And in
Okay.
fact, if you want better performances, usually you like the camera to see further away, so you would like it to be higher. But I think this was a good compromise between seeing further enough and not having something too fragile. Also, because if you have higher the camera higher up, then you will have also this piece of 3D printed plastic would be more fragile.
Okay, thank you. And I also see that when doing the very simple reward function, you say if to check the car is within the track, if it is a yes, then you give it like a 1, and then if it is no, you give it like a -10. So this is a bit like a scale, different scale. Is it so? What is the is it? I think this is quite common, but can you explain more? Yeah, like why yes is a 1 and no is a -10. Why
So
it is not a -1?
Here it's just an example, a quick example. So in fact, you could have also yes as +1 and no as -1. But the idea is as it tries to maximize the sum of rewards. In some cases, if you give only negative reward and you don't scale them well, it may learn to hack it. And this is, in fact, I talk more about that on normalizing reward and what's the problem with it in that talk. And in fact, I will especially talk about some cases of how to choose a reward and why is that in the next slide. So I think best is to just go on.
Thank you. Thank you.
But here it was mostly just to it's just an example. Here in practice, you could just have +1 and -1. Any other question, or we can go on? All right. Then we're good to go. So the first thing I started doing, it was about 2 years ago, was learning to drive, but only in minutes. So with like between 5 to 10 minutes in simulator and 30 minutes in real life, and mostly because my car is 20 years old and there's a lot of play in the steering, which make it quite challenging for driving. And there's different challenges with learning to drive with that car. So first, you have a very small amount of sensor. You just have a camera or just speed information. You have a high variability in what you get in the image. You can have different lighting, you can have shadows, you can have other cars, you can have people around, and everything, all those aspects will affect what you can see. And in fact, when I first started working on the RC car, I did some classical computer vision, and handling different lighting was the hardest problem. Because you can have something that work well indoor, but as soon as you get outdoor or with different lighting or with shadows, it breaks what you created. And then there's some challenges associated with the fact that it's embedded, so it's a Raspberry Pi embedded on it. So it has limited computing power, and you may have some communication delay over Wi-Fi, or with the simulation you may have communication delay because the simulation is asynchronous. And the car is very easy to, it's quite hard to drive just with a keyboard, and it can oscillate quite easily. And as I mentioned, because it's a robot and everything run real time, we want it to be sample efficient. It means that you don't want to train it for days. You want it to train in minutes or hours if you can do that. And one of the main components of doing that is decoupling what's called feature extraction from policy learning. So feature extraction is extracting relevant information from the image in making it low dimensional. And policy learning is the controller, is learning to steer and to drive given some input. Usually in reinforcement learning, people are learning that end-to-end, which means directly from raw pixel, it can learn to drive, but it takes a lot of trial. It takes more computation, and you're not sure that it will be robust. Like if it doesn't learn or if it fails, you are not sure of what's happening. And you will need to train it for many different settings to be robust to many different lighting. So that's what I did. And the main part, so that's called state representation learning. So the part of learning low dimensional representation from images, it's called state representation learning. And that's been, in fact, my part of my research for 1.5 years. And what I'm using on the real car is something quite simple, but also quite effective. It's an improvement of autoencoder. So an autoencoder is just a model. Well, it's a category of model that try to reconstruct an image. So as input, it receives an image. Then it encodes this image into a low dimensional space, so what's called the latent representation. So at the end, you get a small vector, and from that small vector of features, you try to reconstruct the original image, which is what you get on the right here. And the main challenge is because here you have an information bottleneck. You need to compress and only keep the relevant information. So to be able to reconstruct the full image, only given minimal information. And to make it more robust, I do what's called an augmented autoencoder. So I augment the image by adding shadows, by changing the color, by removing some part of the image. But I still ask the autoencoder to reconstruct the initial observation. And that's what you see at the top row. On the left, you see the original image. Then you see the augmented image with some different shadows and different color applied to it. And at the end, you see the reconstructed image. And what you want this model to do is that it will encode the relevant information, which is in that case, the angle of the line and the position also of the limits of the track. And you can see, at least here, it has, even though it has gotten a corrupted image as input, it still reconstructed the relevant information, and that's enough to drive. Here is the example of what you can get with a real car. So on top row is the original image with a big highlight from the sun. Middle row is the augmented image here with some motion blur and Gaussian blur. And bottom row is the reconstruction. So it managed to reconstruct the image quite good. And here the image is cropped because part of the image is not relevant for driving.
I have a question.
Yes.
So how do we verify the reconstructed image accuracy? How do we know, okay, this reconstructed image is good?
So that's a good question, and there's different way. One way is exploring the latent space, so exploring what was learned, and reconstructing the image from that space and just playing around. And here you can see that some dimension encoded the angle, some dimension encoded the lightning. And the way I'm doing it usually is I have you can directly also have a set of images that you can ask to reconstruct, and then you see if it reconstructed them well or not. And when you drive around the track, I have a debug, I would say, window which show me the reconstructed image at all times, so I can see in which area of the track I should collect more data, in which area it's okay. And obviously, you have some loss that you can take a look at to know if it lost enough. But usually, what you can do is on the training set, take a look at the average error, and during when you drive around, you can compare the reconstruction error to what is expected. And if it's too high, then you can save that image and retrain later on. That's it. And the nice thing about this method is you don't need to be a good driver. You just need to collect to have representative images of your environment, of the training distribution.
I have a question.
Yes.
So what loss do you use for the image reconstruction? So do you use like MSE?
Yeah, so I just use the simple mean square loss. I could use something more advanced like perceptual loss. So having a loss on feature of a pre-trained model, but MSE is already working quite well.
Okay, thanks.
And was my answer to the first question enough to know if the autoencoder was how to know if the autoencoder was good enough?
Yes, thank you.
Okay. Any more questions? So maybe one thing I should add is using that type of autoencoder is just one way of learning representation. You have many different way of doing that. But this one is this one is also forgetting everything about action and reward, but you could also include them, and that's what I've been also trying some years ago. If you want to learn more about that, it's called State Representation Learning Toolbox, or SRL Toolbox for short. And also recently there have been some interest in learning good representation without any labels. Okay, so how do we define the reward for learning to drive? Here, usually what I do is I divide my reward in two types. One type is primary reward and one type is secondary reward. So primary reward is what I really want to achieve, and secondary reward is some nice to have thing. So in that case, for driving, the primary reward will be about staying on the track. And what I would like, in addition to stay on the track, I would like to also have some smooth driving. And one issue you may encounter with RL is called reward hacking. Like, for instance, if you say, okay, I want to drive, so let's just maximize the distance traveled, because this should be a good proxy to learning to drive. Because if I drive, I don't know, a lot, it means that it stays on the track enough. The problem is if you do that, it will just learn to zigzag, and it's not something that you want, because to maximize the distance travel, it can just go to, just oscillate. So you may think, okay, we can also just give bonus for every step without a crash. The problem is if you do so, it can learn to just do nothing, so stay on the track with minimal throttle and go slowly or not go at all, because it won't crash, but it won't drive neither. And the same thing goes for the continuity, for the smooth driving. If you try to minimize the steering difference and you give too much weight to that reward, it will also learn just to do nothing, so no steering, or to have a constant steering. So what is a solution to that? One solution is to have a mix of reward. So for instance, for learning to drive, what I did was giving a +1 for every step without a crash, so without a user intervention, and adding a bonus for using the throttle. Because I did not have any information about the speed, I had only information about whether the agent was using or not the throttle. And then the reward was a negative, a constant negative. And in addition, if it was crashing with high speed, it would be even more negative. The idea of having a negative reward which has a higher magnitude than the positive one is to really discourage those type of behavior. Otherwise, it may learn to do some risky behavior if the negative reward is not high enough, because it may compensate the negative reward by all the positive reward it gets before. So by giving a higher magnitude, that's how you try to incentivize it to avoid risky behavior. So this is mainly for learning to drive, but you still need to, if you do so, you will get what's the agent on the left, which is working. It drives, but it's still quite shaky and jittery. So what I did as a first trial was clipping the difference between the steering, between each time step, the steering difference was clipped. So it worked quite well, but it avoid the car to work on some very sharp turn. Another thing that you can do is penalize the agent with a continuity cost, which is simply taking a look at what was the previous steering position and ask the agent to have a smooth transition over time. The problem is, if you do that, you need to be very careful with what's called the Markov assumption. It's one of the assumptions that reinforcement learning uses, which means that the reward that you get at one time state should be only dependent of the current state of the current observation plus the current action. If it depends on the previous time step, you should also give that previous action as input. Otherwise, you break assumption and things may not work at all, or it may injure the performance quite a lot. So this was for the reward, and still there's some termination condition. So the termination is when I terminate an episode, when I terminate a trial. I terminate it on a crash or terminate it on a timeout, so when the episode is long enough. And the timeout need to be handled a bit differently in the algorithm, but that's more or less a detail, and that's done automatically in the case. And regarding the code, I've been using the stable baseline library, and in fact the PyTorch version now, the stable baseline 3, which I'm maintaining. So it's a library, PyTorch library of reinforcement learning agent that provides reliable implementation, that is also user-friendly, and it has active community and extensive documentation. And for training, I'm using the training framework called the RLZoo, which allows to easily train an agent and save all the parameters and checkpoints and then continue training, for instance. And the algorithm in particular I'm using is called truncated quantile critics, TQC for short, which is improvement over soft actor critic, SAC. And I chose it because it's an algorithm which is quite sample efficient. If you want to learn more about that, you can take a look at our documentation and at the paper. So I just want to show you how it looked like as a result. So there's already a blog post and the code is online for learning to drive. But yeah, but the code is now 2 years old. But the code is very similar to what I'm using currently. It's just a bit old compared to what it is, and it's using TensorFlow. So overall, how does it look like? At first, the agent drives randomly, and I stop it as soon as it go off the track. And after some trial, it has learned to drive more and more. So here in the video, you can see also the input image and the reconstructed image. So I can also monitor what's learned. And after some minutes of training, it has already learned to follow the track quite well. It's not perfect yet, but it's only 3 minutes of training. And so I've applied the same method with to a real robot. And this is what I would like to show you now. All right, here it is. So this is after 30 minutes of training. The track is really rough. It's in my flat, and there's the sun with quite some highlight there. But still, it learned to drive, and it was also kind of smooth, so it's not oscillating too much. It's slow because it's an old car and cannot steer too much, but it still learns, and it follows a track which is quite crude. Any questions?
Yeah, Antonin, a question about breaking the Markov assumption, which I just learned that we did that when trying reinforcement learning. Can you elaborate a bit more? How do you really avoid using the oldest state of the model? You mentioned you need to give the oldest state of the model of the previous time step into the algorithm as well. I didn't get that. Can you specify that a bit more?
There's different way of doing it, and the easiest way is to use what's called history wrapper, which means that instead of giving only one time step, you give the current time step and the previous time step as input. Let me just do a quick drawing. It should be fine. So usually you give, so you have your, you have your observation at time t, ops of t, and that's what you give usually as input. But here you need to give also the previous one as input, so ops of t minus 1. And I'm also, because for the continuity costs, it needs to know about the previous action. So I'm not only doing that, I'm also giving, I'm augmenting the observation with the action at t minus 1. And you can repeat that for several time steps. Here I've just shown it for one time step. So at the end, here what you have in white is what you will give to the agent at one time step. Instead of giving only this, let me make it blue. Instead of giving just the, well, this violet box, I give the whole all of those informations. Is that clear, or should I explain a bit more?
So you specify that in the algorithm, in the parameters of the algorithm, that you specify not only the actual time step t, but as well t minus 1. So
actually, I'm doing that outside the algorithm. I'm doing like before the algorithm see it. So it's kind of this is a wrapper around the environment, and it's kind of ops prime. I don't know. Ops prime of t is that, and the agent just see this. Just it doesn't know that it's a previous time step. It just see all of this at once.
So it's just some pre-processing and
Exactly.
the agent doesn't think.
So in practice, you can take a look at the RL zoo. It's in utils wrappers, and you search for history wrapper. Here it is. Basically, it's just so, yeah, it's just repeating the observation and giving that as input. It's, yeah, quite simple.
Okay, now thank you. Now it's clear. Thank you.
Have you benchmarked the single state or state represented by the current timestamp versus timestamp minus X? Have you benchmarked? I'm curious to know what your observations have been.
You mean how many do we need, or does it make a big difference?
Just like how better was your state representation or your outcome when your state representation included the previous timestamps?
So it was much better in terms of smooth driving, and it also in my case it was okay for communication delay, but I know also when there's more communication delay, it's also very crucial to have those two. And yeah, it mostly helps for the smooth driving. It can learn to drive with only one time step, but then it won't be smooth. It will just oscillate.
Yeah. Yeah. I don't want to take over, but just want to say, yeah, nice talk. And I actually built Deep Racer, if you're familiar with that. So happy to share my experiences as well, if you'd like on these.
Maybe later. So yeah.
Of course. No, just in terms of single state versus state
sure.
represented by, yeah.
Sure.
But and we have yeah, go ahead.
There was a question in the chat. I say, the video says variational autoencoder. So yes, in the beginning I was using variational autoencoder, which has additional constraint on the representation, but at the end I removed that constraint and it didn't change much. So if it's simpler, usually and if it works as well, I keep it as is. And do I train the encoder further later during the RL phase? So what you can do, yes, is you can retrain or continue training the encoder afterward. And if you do it, and usually the representation change is smooth enough, so you don't have to fully retrain your RL agent if you do so. And I use continuous action because it makes more sense for a robot. You can also at first use discrete action. So instead of having a continuous value of steering, continuous value of throttle, you can discretize and say left, right, or even bin your action space. The problem when you do that is then you need to be careful on the discretization, because if you don't discretize enough, then it will be also very crude control, and you will need post-processing smoothing to counteract that. Okay, so I think I answered most question now. Let's move on. So until then, it was our learning to drive, and this takes some minutes, but learning to race takes much more. So learning to race usually takes 2 hours for having a first racer, and 5 hours to really race faster than a human. And for that, I also added a new sensor, which is a speed sensor, which is just the magnitude of the velocity. And I needed also to update the objective, because the previous objective was only about staying on the track, but here we don't want to stay on the track. We want actually to have the minimum lap time on the track. So the problem is optimizing for the lap time is quite hard, because this signal, before it learns to drive the whole track, it will take quite a long, and then just having a small, a very sparse reward when it does a lap, it may take very long to train. So I found a good proxy, which is maximize speed while being smooth, and I will talk about that later. And it's a very simple way of framing the problem, but it works quite well. And I'm obviously penalizing crashes. So if you just maximize speed, it will oscillate. So I have different ingredients to have a smooth control. So one is replacing the classical way of exploring in action space by something I've been working on, which is called generalized state-dependent exploration, or GSDE for short. And in few words, this type of exploration is just more consistent and give you a smoother action. And this allows you to use the algorithm directly on the real robot without low-pass filter, for instance. And I also directly condition the reward or smoothness. So here, what you can see is that the reward function is scaled by the delta in steering. So if it's steering, if it's changing violently the steering, it will this will scale down the reward. And the other thing that make it work, both learning faster and learning to drive smoother, is instead of giving the maximal control on steering, I reduces the maximal steering to 50%. And this was also a big improvement in terms of training time and in terms of smoothness. And as I mentioned before, to avoid breaking Markov assumption and for using the continuity cost, I added a history wrapper. So this was about the changes in the reward function. And then I did some changes in the termination. So instead of terminating after a crash, I'm terminating a trial after several hits. So it received obviously a negative reward after each hit. But the thing is, if you want to drive the track around, it may hit the track several times, and if you just stop the episode after each hit, it will never do a full track. And I also stop the episode, the trial, and give a negative reward if it's at too small speed, which may happen because here I was giving the full throttle range, so from 0 to 1. And it can just learn to do nothing. And this is the kind of, or if it's stuck against the track, you need to reset the car. And this is why I terminate on low speed. So for the results, this algorithm and what I've been using so far won one of the virtual race on the mountain track, which was quite challenging because of the shadows and because of driving it was not easy. And the car was not better at driving than imitation learning. It was just better at recovering, mostly from crashes. And to show you the result, I would like to show it to you on the car. So here I will just remove the trees to have to see the maximal speed. And I hope that the frame rate won't be too bad with zoom included. So this is the result after 5 hours of training with everything that I've said before. So I'm using TQC, I'm using the zoo, which allow me to quickly test different checkpoints, and also change some environment argument quickly. And here it's maximizing its speed and smoothness at the same time. And this is what it gave you a good racing line. So the nice thing about this method is I could change the track on the fly. It doesn't have a map of the track. I could have an infinite track and it could still manage to drive it. It could also drive on the other side. And I also did some trial where I was learning to drive in reverse. and I changed nothing to the reward function. I only changed what type of throttle the car could do. And in that case, instead of learning to drive forward, it learned to drive in reverse. And I've got, I think, I have a small video about it to show you. And yeah, and the car drive, yeah, way faster than I do. So for every step, it encodes the image into low-dimensional space, and then the controller takes that low-dimensional features as input and output the steering and throttle. And everything was done trained on my laptop without any GPU. And this is also why I'm also using a pre-trained encoder, because otherwise it will take too long, or it will not be possible to apply it on the racing car with just a Raspberry Pi. And to finish with, I just want to show you what can be done if you just change. I changed nothing, so the reward function is still about maximizing the speed and smoothness, but I just changed what's possible for the car to do. And here the car could only apply a negative throttle, so could only go in reverse. And it's much more challenging to learn to drive, but it's still managed and managed quite well until, well, some point in the track, because I've stopped training at some point. And this is also what's nice about reinforcement learning. I didn't need to drive the car at any time. It just learned by itself to race that way and to solve the task in the best way it could. And yeah, at the end, it still crashes. So that was it for me. If you have any question, that's the moment.
Thank you, Anthony. That's was a great talk, very enlightening. We tried to use the race line position and the deviation from the optimal race line, because we have the training data. We have the position data during training, not during the race. Do you expect that if we do it the right way without violating Markov assumptions to be trainable faster, or do you think it's not necessary because as you showed, it's already converging after 5 or 6 hours, as you showed, and we trained for days and it still was wiggling. So I can state it did not function well.
Okay. I don't know, but I would expect it to probably work faster. But in your case, do you really need RL? You could also just do imitation learning on it, no?
Yes, that's right. The problem there is I'm since months now struggling with the correct PID values, and I will try another one because that's really the difficult part. Yeah, but in theory you can use that and just do behavioral cloning. Yeah. If you have the training data set generated by that approach.
Mm-hmm. Yeah. Oh, yeah. Because okay. Yeah, you could do that. But I would expect, I don't know, I never tried it, but I would expect it to work faster because your reward is not a proxy, it's directly what you want to optimize. So it should work in theory, at least. But I never tried, so I don't know. And in fact, I think that's also what some people have been doing. So creating a map and doing MPC to race with the optimal line. This is a nice approach. This works very well. The problem is, so it requires much more memory, more modeling, and it requires you to do to model the track. Like if you change the track, you will need to update your map and redo a map before being able to race again. And that's where the RL just could work on any type of road, or could work reverse without any problem. It doesn't require a map. It's just a reactive controller.
Thanks.
Do you have any other question?
Yes. I saw you just put your car in reality to drive, right? So which track, or do you just use any tracks in the simulator to train the model or agent and put it back into the car? Because I think you didn't reconstruct your home inside the simulator, right?
Oh no. So that's a good question. So the thing is, I'm not doing simulation to real, so I'm not training in simulation and deploying in reality. I'm directly training the car in the real world. And in fact, that's what my research is about. It's directly applying reinforcement learning on real robots and not, so I don't have the gap between simulation and reality. I'm directly training on the real robot.
Okay, so that means that our agent is not trained inside the simulator, right? Does it take a
No.
lot of time to do that?
Well, to drive it, it was okay. So I mainly stop the car with a keyboard when it drives off the track, and then I drive it back. But as I said, it took, at least for that car, it took 30 minutes, mainly because of all the play that you have here, and it's not even symmetric in the steering. But in theory, it could take 5 to 10 minutes, because what I was doing in simulation was exactly the same that I did in reality. So it didn't take too long to learn to drive, but learning to race would take much more time, yes. So there's a question saying, is it common practice to stack multiple frames to mitigate MDP property? Yes, it's common practice. So that was done in the DQN paper to do some frame stacking. But in addition to frame stacking here, I'm also giving the previous action because I want to have a smooth control. And in fact, in early DQN paper was using differences in observation, not only stacking the observation, but just using the difference between each observation. Do you have any other question?
Yeah, I have one. Actually about the simulator. So do you imagine in like a near future where the simulator would be more realistic and more physics accurate? Would you imagine maybe having a simulator model and doing sim tutorial? Do you imagine that it's possible one day, maybe in like 5 to 10 years, to be able to do that?
I mean, it's possible in theory, and people have been doing that with other type of robot. The tricky part is, there's two tricky parts. One tricky part is having a model of the car which is quite accurate and adding probably some noise. And the other part is randomizing your simulation enough so that you are robust to your modeling inaccuracies.
Okay.
But it should be possible in theory, but it may require quite some engineering, and you need to probably change the visual of the track need to be changed for depending on which location you are, and also you need to match the camera setup with what you have on the rear car. It's possible, just some engineering on that. So that's also why I'm also focusing on learning directly on the rear robot, because you don't, if you don't need that, then you're good to go on any type of robot directly in the real world.
Does pre-training works? I mean, if you pre-train a model in the sim and you just ran some few more episode in real life, would that work? I mean, does pre-training works in theory?
In theory,
in practice.
In theory, it should work. In practice, I did not test it. But here, in that case, you have two mismatch. One mismatch will be the visual observation, and the other mismatch will be the car dynamics.
Yeah, all right.
And normally, in theory, if you can match the two, then yes, you could pre-train and fine-tune there. And in fact, I've been working on pre-training with behavior cloning and then doing some fine-tuning with RL. It's not completely successful yet, but it's a bit encouraging at least.
Okay, thanks.
How do I stop the car when it goes rogue in real robot training? Well, first I don't use full throttle in real life. And then I just need to be very fast to stop the car so I have a keyboard shortcut that will just stop the car if needed, but there's still some inertia, so it still bumps a bit into things around. So you need to have also a car that is a bit robust to shocks, unfortunately.
Yeah. No, thanks. Yeah, no, that's fun. Like I've considered that, like tying a rope and so, something that allows you to really yank and stop and not make damage, right? And
Yes.
actually, so curious. So, was your answer previously to is that completely random to start with, or does it have any idea of the world yet when you start training?
Okay, so what I've been doing so far was learning from scratch, so it has really no idea about anything. The only thing that knows a bit about the word is the encoder, so which is a part of transforming image to low-dimensional vector that represents something interesting about the word. This is mostly what's there at the beginning, but otherwise the controller is completely random.
Got it. And do you have, I mean, have you always done that, or do you have results on first having the sim to real model and then fine tuning, or learning as you go there?
So I haven't done much experiment in for real, mostly because I was missing a track and the track was in my flat, so I didn't keep it too long.
Yeah.
So I cannot really answer your question, but I would like to have a track, yeah, and do more testing in real life. And I would like to also have a better car, but yeah, for now we'll keep the one that I have.
Actually, one thing, last question, like, have you considered, like, with a smaller car, perhaps, that gets you, if all you're interested in starting or learning on the robot directly, have you considered a smaller car that just, that way you get more space and flexibility?
I don't know. I just need a car that I can hack easily, and that I can modify. I not really considered that.
Okay, yeah, maybe, yeah, if space is a constraint, like I'd built a Raspberry Pi bot, like with I believe a 1/24 or 1/28 scale, which was pretty nice, especially in a constrained apartment space.
Yeah, but I think the main issue is not the car, mostly the track.
Yeah.
And I
Yeah.
like to have also a car that can go fast and not just have very small toy.
Sure.
Antonin, I have another question. Imagine an optimal world where you have a neural net that gives you either in the real world or in the sim the track. Would you expect the agent to be trained in the sim, and then directly, do you think it could be applied to the real world and vice versa? Because well, you have the information in a more abstract way of the left and the right lane. Do you think that that could be possible?
Okay, I'm not sure. So you are saying, like, if you can give to the agent a representation of the word that is independent of simulation,
Yeah.
should it work in real world? Yes.
For example, take the comma AI code
Mm-hmm.
and apply it to the sim. Well, it is applied to the real world already, and well, get these kind of information of left and right lane out of the code, and then use that with reinforcement learning. Because then you have the information about the track.
Sure.
Do you
I mean,
see that as possible?
Sure, if you have a representation that is independent, that's the key of having something working also both in simulation and reality, or on different environment or on different track, because If it's invariant, if the agent doesn't see any difference, it should work. The main issue currently, I think, between simulation also and reality would be to model the car dynamic accurately also.
Okay. Yep. Thank you.
So I have a question for you, Anton. So what is the next step after that? So you train a model for the simulator, you train a model for the a 110 scale car. So what do you want to do after, and do you have any improvement ideas or
Sure. So there's many things to do, and I don't have the time for it. But what I've been investigating, so learning to race in hours is nice, but it's still too slow for me. So I would like to take it down to 30 minutes or even less, so I can also have it in the real world. If I could manage to learn to race in just 30 minutes, that would be perfect. And for that, I've been investigating different things. One thing is called offline reinforcement learning, which is you collect some data, and instead of interacting with the word again, you just use that fixed data set to learn some controller. And the nice thing about that is it's different from imitation learning, because you have, in addition to observation and action, you have some reward information. So even if your driving was suboptimal, the idea would be that because you have the reward information, you could still learn something better from it, or you could at least learn to recover. And that's what I've been investigating, and I don't have much time for that, but it's not really successful yet. The other thing I would like to investigate more is like this representation. You have many different ways of doing it, and I would like to try out different other representation, because maybe there's some representation that are much better to train. As I think it was Rainer which proposed, for instance, having some lane representation. That would be also nice, but I think quite some work. But I'm thinking about trying other technique of unsupervised learning or self-supervised learning for that. And then also, to make learning faster, you could also learn with multiple robots at the same time. And I've been testing that for another project, and it's quite interesting of what you can possibly do with that.
So yeah, it just made me think about something. So have you actually tried maybe car avoiding and overtaking?
No, not yet. But the nice thing about car avoiding is that even though it is trained to not reconstruct everything that goes into its vision, so if you put a car in front of it, it won't see it, because the autoencoder is reconstructing the clean image. But it still changes the image, and the car slows down by itself because the image is more noisy. But that would be, yes, one way would be to train different experts. One expert to overtake, one expert. What were you saying?
Yeah, to overtake and avoid.
Yeah, to avoid. The idea would be to have some hierarchy in it. That would be a solution, but it's quite a lot of work, and I don't have the time for that. So
Okay.
yes, but it would be nice if someone else was doing it.
Would it be easier, for example, to have a pace car, so a car moving slowly on the track, and you just have to deploy your model? Would it be better, or
I mean, I could just, yeah, in fact, I can already do that, because I can just use a car and limit the throttle and leave it on the track, and then train it as usual, because if it hit the car, it will get negative reward, and if it hit the car, it will also slow down, so it will learn over time to probably avoid it automatically.
Okay.
So that would be a solution, in fact, without changing anything to the reward. It would just change the environment.
But I think it's still, I mean, it will also make the training longer.
Sure, but I would probably do that after that I have already an expert or something.
Okay. Oh, and I think we have a question in the chat.
Are you talking about offline RL essentially? What do you mean? I think I've answered that.
No, that was previous.
Okay.
That was a long ago. Ignore it.
Okay.
Anthony, another question. We recently learned a new algorithm from a colleague in the Virtual Race League called Augmented 2 that is somewhat similar to reinforcement learning. Have you digged into that? And because I understood that it can learn quite fast in terms of minutes. Have you digged into that?
I'm not sure what you're talking about. Do you have a link or do you have?
Yeah, I can post the link in the chat. One moment, please.
But RL overall is just a general framework. There's many things included in it. And here, what I didn't say is I mainly talk about model-free reinforcement learning, so where I'm not modeling the dynamics, but there's some work also on model-based reinforcement learning.
So I posted the link, so maybe something we can talk about later.
Yeah, I will. Yeah, probably take a look later. No, I have no. I don't know that algorithm at all.
I also have a question. So when you trained your RC car with RL, typically like how many episodes did it take?
You mean to drive or to race?
Just to drive.
Okay, usually I prefer to talk about hours because an episode can be 2 seconds. Like if it crashes after 2 seconds, it's 2 seconds, or if it does one track, it's 45 seconds.
Okay.
But I think, yeah, I need to check again my logs, but I prefer to talk in hours. And in hours, it's 2 hours to have already good driving and 5 hours for very good driving.
Okay. Have you tried experimenting with like different dense layers for the RL after the reconstructed image? I mean the latent representation.
So I'm mainly how to say that. Until now, I was mainly limited by my laptop, which had to run the simulation plus the RL training and the encoder on CPU only. So I was only using the minimal amount, I would say the minimal network. But usually having a network that is slightly wider gives you faster and better training, but I did not have the time yet to experiment with it. The good news is recently I got a better computer, so I should be able to try with heavier computation, I would say.
Okay.
But most of the work is done by the encoder, so you don't need a network more complex than the two-layer one, and 200 units per layer. Usually that's what I'm using, and it's already working quite well and fast.
Okay, because I read somewhere that if you have a wide layer, it tends to memorize the information quickly at the cost of overfitting. And then it doesn't learn to generalize. But then if you have like a deeper layer, then it learns to but it takes longer, not overfit, but.
So the thing here, the overfitting is limited because the encoder is fixed and the encoder is invariant to the different augmentation that I'm doing.
Okay.
Which means that if it overfits this representation, then it's usually good news because it should, in fact, generalize, not because it has learned to generalize, but generalize because the representation is general enough.
Okay. So it takes you like 2 hours of resetting the vehicle to have it like roughly drive with SAC?
2 hours to race, to do a full track that is not crashing and that is okay, but not the fastest lap. But yeah, it's 2 hours, yes.
on the actual RC vehicle or in the simulation?
No, in simulation, I do not have the track nor a good car and a good enough car for. But I would like to test it in the real world, but I did not have the opportunity to do it. And if in fact, if someone wants to try it, I can also collaborate and open my code for that.
Okay, because I'm Jesse actually. I'm the guy that tried with the Raspberry Pi 4B vehicle. So right now I have DDQN on the Raspberry Pi. I got like a latent dimension of around 32, and then I have like one dense layer of 512 with like a action space of like 5 action spaces. So I'm trying to like simplify the RL algorithm as much as possible, but currently it doesn't train in 30 minutes and like resetting takes a long time. So I was wondering if you had any like more practical tips for it.
Yeah, so what I do when I reset, it's trained in parallel. So when I reset the car, at least on the real car, it's training in parallel. So I don't lose any time during that.
So when you trained with your RC car, did you have like the training done in the laptop and then, or everything was on board?
Yes, no. The thing is, I was using my laptop for training because otherwise the Raspberry Pi is way too slow for that. And I was communicating only the compressed image over networks, so to reduce the bandwidth.
I see.
And then the nice thing about that is later on you can deploy the train agent directly on the Raspberry Pi. But yes, the training was done on my laptop. Even it was communicating over Wi-Fi to the car.
Okay, I get like an action rate of like 1 hertz when I'm actually training right on the RPi. But
yeah, I was around 10 hertz when I was doing that.
Yeah. Okay. All right.
Thank you. So yeah, thank you. So there's a question in the chat of where can I find your latest way to try it. So it's not open source yet. I'm still cleaning it, and I was planning also to do several videos to explain how it works and to build it from scratch together online. But overall, most of it is already open source, which is a stable design library and the RSU. The only not open source part is the code for training the autoencoder and the code for collecting data, and the code for and the exact code for the reward. But here I gave all the information about the reward function, so you should be able to reproduce it. But I plan to open source it soon. I'm just finishing cleaning things. It took some time also. Yeah, I will probably advertise it, and I would like to do in fact a stream, so directly go on Twitch to do it, so it forces me to to do it fast. But it still requires some preparation, and yeah, it's I cannot just start streaming and do things, otherwise it will be very, very long. Okay. Any more questions? I think we are already quite past, and we have many people that had to drop because the time zone. It should be midnight in some places now.
Yeah. So if we have no more questions, thanks a lot, Antonin. It was really great. So yeah, it was really cool. Thanks thanks for sharing your experience and your knowledge about this subject. And yeah, if you are watching this video and you want to reach out to us, don't hesitate. We can organize that. So at any time when you're okay to do it. So yeah, thanks a lot.
Thank you, and goodbye then.
Thank you. Thanks a lot.
Yeah. See you.
Thank you. Bye.
Bye.
Thank you.